into the second presentation today, I just want to repeat also the congratulations to the Access team. Very hard to express how excited I am about this news. Um, so yeah, congratulations. And this is not an image that reflects in any kind of way the feeling I have about this, but I put this up usually when I talk about this topic to demonstrate what I mean when I talk about dust scattering. So this is a picture of St. Peter's Cathedral. At any given day, you will see that it looks kind of like that, filled with people and filled with light. But if you wait for the right time of day, with the sun in just the right position, this is something you might see, right? And so what you see here is obviously a demonstration of dust scattering with particulates in the air scattering sunlight into our directions. And we see both that there is sunlight coming in from some direction. We also see that there's dust in the air. And in principle, we can use this information to determine where the dust is and how much of it there is. So this is the principle behind dust scattering. And so the technology we've been developing as a field is what I would term as X-ray dust tomography, the 3D study of dust distributions and the characteristics of dust using X-ray astronomy. So title is X-ray dust echo tomography. It's kind of long, a new era of galactic exploration with Access, and there are a lot of collaborators. I won't read them all, but I do want to point out the Swift GRB 221009A team, as well as Leo Corrales, who have been very closely collaborating with me on some of these things. Okay, so want to acknowledge, of course, support by NASA and NSF as well. So dust scattering, what is the punchline of my talk? I'm going to try to convince you, hopefully successfully, that this can be a killer app for Access. There's a real exciting possibility to do entirely new things and to go much deeper where we have already scratched the surface with Swift, Chandra, and XMM. So what is the science that we can hope to accomplish with this technique? So it allows us to map out dust distributions in the Milky Way in 3 dimensions. So we can measure distances to dust clouds, in principle only constrained by our knowledge of the distance to the background X-ray source. And then we can use our constraints on dust clouds in the Milky Way to constrain the Milky Way structure by itself by comparing it to observations at our wavebands, most notably in CO and in the infrared, where extinction mapping allows us to, at least nearby, make very good dust maps in 3 dimensions as well. And in addition, we can then also hope to measure distances not only to dust clouds, but also to the X-ray transients inside the galaxy that cause the dust scattering that we see. And ultimately, we can also hope to constrain dust physics. So we can constrain the dust size distribution, which is important for understanding grain growth and destruction, as well as the mineralogy. So what is the actual chemistry and mineralogy of dust grains? So here is my example of how dust scattering and dust X-ray tomography work. This is my first entry into the field. This is Source X1, the source in the circle here. Keep your eyes on it. This is Maxi. This is the All Sky movie from 2014, 2013, 2014. I'm going to set this in motion, and you will see what happens in the All Sky X-ray sky. And keep your eye on Source X1. So as the time moves forward, we're now in October of 2013. You can see Source X1 flicker, and then it turns back off. And so it became one of the brightest X-ray sources in the sky. Let's play this one more time. So Source X1 becomes visible, becomes extremely bright, more than a crab, and then it turned off very quickly. And so this was the prelude to the observation. So we observed the source with Chandra about 40 days after the end of this outburst. And what we saw is the following. The left image is the one I wanted to show first. Sorry about the mix-up in the order here. So the left image is my view of what Chandra sees, and the right image is what the Chandra PEST office sees when it looks at this image. So what you see here on the left-hand side is, of course, the source itself, the X-ray binary. It's a neutron star. There are structures around it that are interesting to study by themselves, but they're not related to what I want to talk about today. So there's a jet, there's a neutron, there's a supernova remnant. What I want to talk about today are these rings of diffuse emission that were created by an echo from the bright outburst the source had 40 days earlier to the observation. And so Obviously, you can see Chandra's field of view is limited. We don't observe the entire echo, but it's very clear that there are multiple structures visible in this image, and they all have ring-like shapes. So this is what we expect from X-ray light echoes. And so here is how this works in terms of geometry. So suppose we are the observer over here. This is our X-ray source, and we have some dust cloud in the middle between us and the source. So in the case of Solution 1, we did not know the distance to the source, so this made everything much harder. And we didn't know the distance to the source, and we also didn't know the distance to the dust. But in principle, this is how it works. Photons travel from the source in multiple directions. Photons traveling directly to us without being scattered have a shorter path, and so they arrive first. Photons traveling in a different direction, sometimes scattered back in our direction, take a longer path, arrive from a different angle, and arrive with a time delay. Right? And so we see photons scattered in this location up here in the sky. And since this is a sheet of dust, a thin dust cloud, what we actually see is a ring of emission at the same angles. And here, up here in the left, you see the formula for the observed angle on the sky in relation to the time delay between the outburst and the observation, the distance to the source d, and the relative distance between us and the dust compared to us and the source. In this case, we didn't know either of those distances, so that made it a little harder. So here's how this works. Okay, it's a photon. Photons get scattered up here in the dust cloud. We see the direct photon first, then we see the scattered photon second, and we see a ring at that particular angle. Now, the angle depends on the distance to the dust as well, right? The x enters this formula. And so we have multiple clouds, we expect to see multiple rings. So in Solution X1, we didn't know either of those distances, and we had to determine both. So here's how this works in 3D. At any given time delay, all scattered photons have to come from the surface of a scattering ellipsoid, right? If you have a shape between two focal points where the distance, the cumulative distance between the two focal points and the surface of the object is always the same, that's an ellipsoid. And where the ellipsoid intersects dust clouds along the line of sight, we get enhanced scattering emission, and so we see multiple rings. And this is exactly what we'd see in the case of Solution X1. We see 4 rings at least, and so we see 4 dust clouds. We can infer the relative distance to the dust clouds, but without knowing the distance to the source, we don't know either. So in this case, we were able to do some detective works by comparing the scattering emission to CO. And so specifically looking at, and this is now an XMM observation of the same echo, by looking at where X-ray scattering is bright versus where it's not bright, comparing that to the CO, we can fingerprint individual rings to different CO clouds. So here is such an identification. The innermost ring here is paired to this CO cloud at that particular galactic rotation velocity. And if we do this for all the rings, we can constrain the distance to the source. And here is the posterior distribution. And we find that this distance is about 9.4 kiloparsecs plus or minus 1, compared to a distance ambiguity between 5 and 15 kiloparsecs before this measurement. Okay, so we were able to constrain the distance to the source, and that allows us to then also constrain the distance to the different dust clouds. And so here's our dust column density distribution based on this distance determination. We have 4 clouds at different distances. Column density is plotted in here. It does depend on the scattering cross-section, but now we have a distance to the source in kiloparsecs and a distance to the different dust clouds as well. So this is hard because we didn't know the distance to the source, but it can be easier if we observe an echo around a source for which the distance is known. So in this case, the source is V4 Cygni, which has an exquisitely well measured distance from VLBI parallax. And so in that case, in 2015, there was an echo, which we also observed with Chandra and Swift, that allowed us to directly measure the distance of the different dust clouds. So here is, on the right-hand side, we see the Swift composite image of the echo. And on the left-hand side, you see the light curve of the outburst from the source, which was very nicely brief in time, which allowed the rings to be very narrow. And given the known distance to the X-ray source, we now can translate directly the angle and the time delay on the image at the right to the distance to the different dust clouds that produce the different rings. So there are at least 8 rings visible in this image. Here's the Chandra observation of the same echo. Obviously, the field of view is limited, but you can see that the resolution makes a big difference. So here is Swift, here is Chandra, so the resolution, as I will show on the next slide, is actually very important if we want to do a good job of constraining where the dust is. So the The two histograms in black and red show the distributions we derive from Swift in black, right? This relatively broad distribution. And in red, we see the dust distribution from Chandra, which is exquisitely accurate in determining the distance to each of those dust clouds. So now we have an extremely good representation of where the dust is. It's broadly consistent with the infrared dust distance measurements from extinction. So angular resolution is critical in this case to determine accurate distances to the dust clouds. So we can measure dust clouds in 3D because we have images of the dust clouds, right? These intensities have angular dependence. We can measure their distances. But I said we can also constrain dust mineralogy. So on the left-hand side, I show different dust scattering cross-sections for different dust models as a function of energy and as a function of scattering angle. And different models have measurably different cross-sections as a function of these two variables. And if we then fit the echo intensity to these different models, we can constrain, which is shown on the right-hand side. I don't expect you to see this table, but we can constrain different dust models. And in the case of V4 Cygni, what we find is that actually a typical MRN, Mathis, Rumpel, and Nordzig dust distribution fits the data rather well. I'm a big fan because the MRN distribution was developed right here in Madison, and so that was a lot of fun to do that work. So I'm going to skip through this table and get to the third use case. So in previous two cases, we were looking at galactic X-ray transients. So these are X-ray binaries within our own galaxy. But you will probably all have heard about GRB 221009A. And in this case, the geometry is extremely simple, right? So if we're looking at dust echoes from gamma ray bursts, we know the distance of the gamma ray burst because it's effectively infinite. So the geometry becomes extremely trivial, right? So the source is in this direction. All the light coming in is parallel because it's a cosmological distances. So all the scattering happens within the galaxy. And so we can directly translate the observed angle to the scattering angle, which is the same. And the geometry now simplifies the distance measurements tremendously, right? There is no more relative distance. We just measure the distance to the dust directly by measuring the angle and the time delay. And because gamma ray bursts are very short, this works exquisitely well. So here's the light curve of GRB 221009A. Obviously, this happened on the 9th of October in 2022. It was this gamma ray burst was called the brightest of all time, the boat by Eric Burns, and it was truly the brightest of all time. And we'll show you log n log f in just a second. But it was a long gamma ray burst, which means that the time duration was about 100 seconds for the whole thing to develop. It had a very large fluence of 3 × 10⁻² ergs per square centimeter, which is larger or rivals the fluences of the outbursts of these galactic transients. It was at a galactic, fortuitously, it was a galactic latitude of 4.25 degrees, so close to the galactic plane, and with a peak flux of 0.1 megacrab. So that is pretty incredible. And the galactic column density is about 5 × 10⁻21 per square centimeter. So here, as I said, is the log n log f. So it's the distribution, the cumulative distribution of fluences. So the fluence is the time integrated flux. It's the total energy per square centimeter arriving at Earth or at the top of the atmosphere. And so this figure from Eric Burns' paper in 23 shows the distribution of fluences for gamma ray bursts previously measured. And it follows this nice relation, and then, depending on the sensitivity of the instrument, it rolls over, but this is sort of the expected log n log fluence. And then GRB 221009A is shown in these stars here for two different instruments. And you can see, right, it's about almost 2 orders of magnitude more energetic in fluence. So there's about 100 times more energy that arrived at the top of the atmosphere than for the previously most energetic bursts. And if you look at what the statistics are for these for this particular burst, it's like 1,000 times, if not more, less likely to happen than the previously observed most luminous bursts. And so this is a 1 in 1,000, 1 in 10,000 year event. This happens only once in about 10,000 years. So is there any hope of doing something similar to what was possible to be done with this particular gamma ray burst? And I'm going to hope to continue that that's actually possible. So it's extremely rare to see something this bright, right? If you just follow the line down to where the expected rate of bursts per year is, it's 10⁻⁴. Okay, so here is the dust echo observed from DRB 221009A. On the left-hand side is SWIFT, on the right-hand side is XMM, just to show two of the instruments that observed this. So it's a beautiful echo. These are single exposures, and you can see many, many rings, which correspond to many, many different dust density peaks in the line of sight between us and the edge of the galaxy. Remember, this is at 4.4¼ degree above the plane. So we're actually not looking through the plane of the galaxy here, but it's still close enough to see a substantial column of dust. So here's our Swift dust distribution we derived from all the Swift observations. There were about 100 pointings or 100 exposures that we combined to derive this distribution. And you can see, right, that we can pretty accurately derive where the peaks are. And you can also see that we detect dust out to about 20 kiloparsecs. Right? So we are looking entirely to the other edge of the galaxy. So in principle, this allows us to measure dust at any galactic distance between us and the edge of the galaxy in any direction we want, as long as we have enough dust between us and the source. So there's a lot more work that is still ongoing to learn more from the dust echo of this particular gamma ray burst, but I want to switch now to what AXIS will be able to do for us. So what does the future of X-ray dust tomography look like, and why is AXIS, in my view, the perfect telescope to carry this work forward? So here are the science requirements to do X-ray dust tomography. We need high angular resolution. I think the comparison between Swift and Chandra for V4 4 Cygni shows this very nicely, just in terms of measuring distances, right? So if we want to measure distances more accurately, this directly translates into a requirement on angular resolution. But high angular resolution is also critical in the case where we're background limited. And this is the case for the lower column densities or for lower fluence bursts or transients, because naturally these are diffuse, the rings are diffuse. And so higher angular resolution buys you a lot. We need large collecting area, naturally. This is always true. So more is better. We need, again, we're background limited. We need low stable background. And so LEO is perfect for that. And so AXIS will deliver. And then we need TOO capabilities, because these happen on day to week time scales after the outburst. And so we need to be able to point our telescope without too much complication into a direction where it would observe the echo. And again, being in LEO and being flexible is really important for making this possible. And as you will all know, it's become very difficult to schedule TOOs with Chandra. And this is one of the main limitations that we face right now in following some of these echoes up at high angular resolution. And then we need large field of view, and larger is better, of course, because these are many arc minutes in size typically when we observe them. And so a combination of all of these is ideal. And then we need sort of secondary requirements that ideally we will be able to satisfy. So we, first of all, need an available all-sky monitor in the X-rays or gamma rays. So right now, Swift has the BAT, we have MAXI, and we will hopefully continue to have monitoring of the sky at X-ray wavelengths to alert us to bright transients that we can then follow up. And then we need, at least in the past, we needed the ability to observe bright point sources. Because if we are looking at a galactic transient, then it's possible that the source might flare up again. And anybody who's done observations like this knows that the instrument people are very nervous when you propose to point your telescope at something that could be several crabs all of a sudden. But for gamma ray bursts, actually, this is not a concern because they do not rebrighten. And so if we follow up gamma ray bursts, actually, this sort of goes away. So here is the prediction for the sensitivity of what AXIS will do in terms of the number of galactic transients that we will be able to follow up. So this is now a few years old, so this might need to be updated with new effective areas, etc. But the contours show the number of sources relative to what Chandra sees or is able to follow up based on effective area and background. And so AXIS is over here to the right, and we know that it's going to have much lower background. So we can probably expect AXIS to increase the number of sources that we would be able to follow up by a factor of something like 30, based on the statistics of point sources observed over many years with MAXI and the RxD all-sky monitor, just based on the statistics of flares of certain fluents within the galaxy. So this was published in 2019, it's a while ago now, so it's time to update this. But so this promises that we will be able to follow up many more sources within the galaxy to do the kind of tomography we've been doing with X-ray binaries like Swiss 1 and V404. So it's a very good outlook, right? And AXIS really sort of ticks all the boxes for galactic X-ray tomography. But I actually think that following a gamma burst is an even better application. So there have been gamma bursts before 221009A. So GRB 031203, for example, on the right was followed up with XMM. And so it is possible to do this with gamma bursts. And as I said, it has a number of advantages. Most importantly, that we know the distance to the gamma burst, and so we can directly translate measurements of angles to measurements of distances. And so what will AXIS be able to do in terms of following up gamma bursts within our own galaxy? And so I'm going to put up the distribution of isotropic energies first and redshifts for different gamma bursts to put GRB 221009A in context again. So this brightest of all time, right, like 1 in 10,000 year event, really stands out in both the fluence, but also in the terms of the isotropic energy. It's one of the most energetic gamma bursts, but we're extremely lucky that it was so close to us. So it's unlikely that something like this will happen again. And the question is, what does the distribution of the rest of these GRB energies and fluences promise in terms of following this up with AXIS? And so here again is the fluence distribution, right? The log fluence log. It's a log n log fluence distribution equivalent to log n log s, but for fluence, which is the relevant quantity that matters for gamma bursts and echoes. And again, the Swift observation I'm using the Swift observation of this echo as our sort of benchmark to compare what AXIS will be able to do based on its capabilities. And so Swift was sort of sensitive down to column densities, cloud column densities of 10 to the 19 per square centimeter in equivalent neutral hydrogen. Which is relatively small, and the sensitivity goes up with distance a little bit just because of the scattering angle dependence on angle, the scattering cross section dependence on angle. And so if we want to see what AXIS will be able to do based on both its effective area, but also the much better angular resolution, and at these column densities, we're background limited, right? This is sort of the smallest we can do based on what we observe. Sort of taking that into account at similar background rates, AXIS will be able to sort of observe down to this kind of level of fluence at the same column density, right? And what is the number of events that we expect per year? Well, it's only a few. And then the problem with that, of course, is that most of these will not be in the galactic plane. So it might not be possible to do many observations down to this level of column density sensitivity, but this is extremely small, right? These are very small clouds, and we are detecting clouds that are sort of hovering above the plane of the galaxy by several degrees. If we look through the plane of the galaxy, we expect clouds to be, the presence of clouds with much higher column densities of something like 10 to the minus 20, and up to 10 to the 21. These are 10 to the minus 20. 10 to the minus 21 is a typo in here. Sorry, not a typo there, 10 to the 20, 10 to the 21 per square centimeter. So the cross sections work out so that that's sensitivity that you observe at those fluences. And so if we follow, an observation of clouds that have sort of these column densities that are a factor of 10 to 100 larger than the minimum column we observed with Swift and XMM for GRB 221009A, then of course we can go down to much lower fluences, and the numbers we then expect are sort of in the tens to hundreds per year. Of course, most of those will not be in the plane of the galaxy, but some of those will be. And so if we just look at the statistics, there's about 7.5% of the sky lie within the 4.3 degrees that GRB 221009A was from the galactic midplane, and then about 2% of all bursts will be at about 1 degree or less compared to the midplane of the Milky Way. And so we expect about 4 per year at equivalent sensitivity. Most of those will not be in the galactic plane, right? So the 10 to the 19 per square centimeter sensitivity, but there are some clouds nearby that we might be able to see. And then we expect to see about 4 per year within about a degree from the galactic plane that we can detect down to about 10 times the column density that we're sensitive to with Swift. And so that was, you saw the column density histogram. We detect most of the galaxy. and about 1 per U that has equivalent fractional sensitivity per kiloparsec. So I hope I convinced you that AXIS is perfectly designed for X-ray dust tomography. This could be a great app for AXIS. There will be lots of work to do, follow up transients in the Milky Way, measuring distances to dust clouds, doing gamma ray burst tomography with many more gamma ray bursts than was possible with current instrumentation. And that, I guess I finished the presentation, and let me put this back up just to show this again so that I can take maybe a question or two. Thank you.
Great. Yeah, that was a great presentation. So I'm wondering now that you've, the GRB is really interesting if you get it kind of right in the plane like that. But are there other types of sources that you might have, like TDEs or ULXs, or I guess
Yeah, so
wouldn't help.
so you need a fluence, right? So to do this, we need fluences. If we go back and we look at the fluence distribution, right? So this is sort of the range where we're going to be sensitive. And so, right, so this is extremely rare. I mean, even galactic transients don't reach these kinds of fluences, right? This is bolometric, so this includes gamma rays, but even in the X-rays, right, it's maybe a factor of 10 lower. This is extremely rare, even for galactic transients. But going down to lower, to lower fluences, right, we'll be able to pick up potentially other sources that we haven't studied before. So actually, it's a good question of what the maximum fluence of the TDE distribution actually is. I haven't actually looked at that, and this is probably worth following up. Maybe I'll talk to Kara about that. But yeah, so I mean, this will potentially open up other sources to find potential dust echoes for. I would say certainly from the historical experience, there are enough galactic transients, and now it looks like there will be enough gamma ray bursts to do very interesting follow-up signs. So that's sort of the limitation, right? So we have to have something that has fluxes that are, peak fluxes of the order of, Crabs to tenths of Crab, and or fluences that reach these levels.
Great. So are there other questions?